Hello, AP Chemists. So in today's video, I'm going to introduce some thermodynamics topics. Today, I'm going to discuss entropy. So first, I'm going to look at thermodynamic favorability. We have looked at several chemical processes so far in this class and have found that going towards a lower energy state is more stable. Okay, we looked at that when we looked at bond formation and also when we've looked at chemical reactions. This would make us think that all exothermic reactions occur because the energy is lower in the products, and all endothermic reactions do not occur because the energy increases as it is absorbed. But that's not the case, right? Because we see endothermic processes occur. So what else drives the reaction? There are other factors that we have to consider. One of those factors is the activation energy. So the activation energy is the energy that goes in to break bonds and get the reaction started. So a reaction might be favorable, but it doesn't happen unless we apply enough energy to get it started. That energy would be called the activation energy. We would call this kind of reaction being under kinetic control. We will talk about kinetics in a future unit, but we call this being under kinetic control because even though it's favorable, the rate of the reaction is extremely low because of a high activation energy. The thing that we are going to focus on today, or the reason that reactions may be favorable, is entropy. Entropy, which we are going to abbreviate with the capital letter S, is a measure of the disorder of a system. We may also think of this as randomness, or how much the particles are dispersed. More dispersal or more randomness would mean greater disorder and a greater entropy. Having greater disorder is favorable. Okay, so the second law of thermodynamics says that the entropy in the universe is always increasing. So anything that leads to greater entropy or disorder in the universe is going to be favorable. Going towards greater disorder is a positive delta S. And we know that when we think about a delta, right? So when we have delta, we know that that's final minus initial. So if the final entropy or the entropy after the process occurs is greater than when it started, then it went to greater disorder, and we would say a positive delta S. Lesser disorder would be a negative delta S. So if we were to look at these three different situations, so they're all oxygen. We have solid oxygen, liquid oxygen, and gaseous oxygen. We can talk about their entropy, right? The one that has the most disorder would be the one that has the highest absolute entropy. The one with the greatest order, or the least disorder, is going to have the lowest entropy. So we are going from low entropy to high entropy as we are going from solid oxygen to gaseous oxygen. Another thing that's going to be important for us with entropy is that having more particles means an increase in absolute entropy. So the way that I like to say this is when we have more stuff, then it is more disordered. And that makes sense, right? At the beginning of the school year, my classroom was immaculate, and now it is a hot mess. As I accumulate stuff throughout the school year, we see a greater amount of disorder in my classroom. Here's an example that actually relates to chemistry. Here I have this molecule, and we see the reaction for its decomposition. And I'm going to tell you the entropy here is increasing. But let's look at some reasons why. One reason why it increases is we are going from 4 particles, or you can think of it in moles too, of reactant. And we end up with, I think it's 29 particles in the product. That's more stuff, so there's more dispersal, there is more disorder. The arrangements of all of those products is going to be greater disorder. Okay, so that is one reason that we are going to look at. Another would be that we are going from having only liquid in the reactants to now having gas. Okay, so we had no gas to start, and then we have gas in the products. And we know that gas particles can spread out a lot more. That's something that we know. I like to also think about this as the number of gas particles. So we're going from 0 gas particles, or 0 moles of gas, to really all of its gas. So we're going to 29 moles of gas. That's honestly the most important factor of those. We always are going to look at the moles of gas. Entropy is also going to increase when volume increases. When there's more space, as we can see in the picture to the right, there is a greater dispersal and randomness, or a greater entropy. Entropy is usually going to increase when we make solutions with solids and liquids. So what I mean by that is that if I dissolve a solid into a liquid, usually we are going to have an increase in entropy. An ionic compound, and in particular an ionic solid is what I mean, it's highly organized in a crystal lattice. We've talked about how rigid that is and how there's no real movement of those particles past each other. But when I dissolve it, we see that the particles are able to spread out in the solution, and there's also more randomness to it. And so we see that there is an increase in entropy. Another factor that would increase the disorder in a system is to increase the temperature, which would be by adding heat. When the temperature increases, then the entropy is also going to increase. You could think that those particles are moving more, and they're also moving with higher average kinetic energy, so they're like moving faster on average, right? There's a lot more movement going on. That increases the amount of randomness in the system, the amount of dispersal, and therefore the amount of disorder. Here I just have a reminder from before where we have our Maxwell-Boltzmann. Okay, our Maxwell-Boltzmann diagram, where we have the kinetic energy of the particles labeled on the x-axis and the number of molecules, or the fraction of molecules, on the y-axis. We can see as the temperature increases that the peaks are going to flatten out and move to the right. Okay, so they flatten out and move to the right, meaning that there are more particles with higher kinetic energy and then therefore greater speed. So it's really important that we are able to predict the sign of delta S. This is a very typical question in this class and shows a good understanding of knowing when a system goes to greater entropy or less entropy. What we are going to do to predict the sign of delta S is we are going to look at the balanced equation. In particular, I want to look at the number of moles of gas. Okay, if the number of moles of gas in the products is greater than in the reactants, then our delta S is positive because the disorder increases. We're going from less gas to more gas. That's more dispersal, more disorder. If the number of moles of gas in the reactants is greater than the products, then we are going to less disorder, okay, because we are taking all these moles of gas, decreasing that number, and therefore decreasing the dispersal, the randomness, the disorder, the entropy. Okay, if the number of moles of gas does not change, okay, if it doesn't change, then you got to ask yourself, does the number of moles of particles change? Okay, so maybe the number of moles of gas is the same on both sides of the reactant, but you still end up with more moles of stuff. That's going to be a greater randomness in the arrangement, and therefore a positive delta S. So if the number of particles goes up, you will have a positive delta S. And if it goes down, you will have a negative delta S because it is getting more ordered. Let's look at some examples here. So this first example, what I'm going to do is I'm going to count my moles of gas in the reactant side, and I'm going to count my moles of gas in the product side. Okay, on the reactant side, I have 1 mole of gas. On the product side, I have 3 moles of gas. So that is an increase in the number of moles of gas from the reactants to the products. So we would say that that is an increase in disorder, and delta S we would predict as being positive. In the second example, we are going from 3 moles of gas to, 0 moles of gas. So we're going from having gas to not having gas. That is a decrease in disorder, and therefore a decrease in entropy, and delta S is negative. In the next example, I'm going from 2 moles of gas to 1 mole of gas in the products. That is also a decrease in entropy, and therefore a negative delta S. The fourth example, I'm going from 1 to 0. Also a negative delta S. The last example does not have gases at all on either side of the reaction arrow, but what I do see is we're going from having a solid, which is highly ordered. I don't know how to spell highly. To something that is less ordered or more disordered. So because of that phase change to where we're going to more disorder, my delta S would be positive. The last thing that I'm going to talk about in this video is how we could actually calculate delta S. So we talked about predictions, but now let's talk about how we can calculate them. And to do that, we are going to look at the absolute entropies of the reactants. We are going to look at the absolute entropies of the products, and we are going to do products minus reactants. Because remember, when we have delta, we tend to do final minus initial. And the final is the products, the reactants are the initial. All right, so let's look at this in action. So here it gives us a balanced equation. We have XEF6 decomposing to form XEF4 solid an F2 gas. One thing that I like to look at with this is what would we think about our delta S? Do we think that it would be negative or positive? Looking at this, I see that we go from 1 mole of gas to 1 mole of gas. So it may not change too much, right? Our delta S may not change too much. But I do go from 1 particle or 1 mole to 2 moles of stuff. So I do think that the disorder increases some. Okay, but let's take a look and actually do the calculation. So I'm going to say that delta S is equal to the sum of the absolute entropies of the products. Okay, this should not say delta right there. It should just be an absolute entropy. Okay, so that should not say delta. Ignore that. Okay, if I am looking at my products, I have 1 mole of XeF4. Okay, and that's just going to be the S of that. I have 1 mole of F2. From that, I'm going to subtract the reactants. I have 1 mole of XeF6. So at that point, I'm going to plug in what I have. So I have 1 mole times XeF4 is 146. F2 is 203. And then XeF6 is 300. I didn't really give myself a whole lot of room here, did I? Okay, and so I'm going to plug that into my calculator. So I have 146 times 1 plus 1 times 203. And then from that, I end up subtracting 300. So my delta S for this reaction is 49. Okay, all of these were all moles. So moles cancel on all of these. So I'm left with joules over Kelvin as my answer. And that makes sense, right? That was one of the things that we talked about. We talked about how we expected it to be positive because we went from 1 particle to 2 particles. And so we expected to see that positive delta S. Let's look at 2 more examples. And I really wanted to focus on these to show you how to use an appendix in the back of your textbook. It's obviously not a skill that you need for AP, for the AP test, because I would just give you the values, but it is important for your future studies in chemistry. Okay, so let's take a look at that. All right, so like magic, I now have an appendix. This is from the back of our textbook, and so I'm going to be referencing it as I do this problem. So the first problem asks us to calculate the delta S for the reaction above using the appendix in Canvas. So what I'm going to do is I'm going to go ahead and write out my formula that I'm going to use. So remember that I do my absolute entropies of my products, the sum of those, minus the sum of the absolute entropy of my reactants. This is a formula that's given to you in your formula sheet for the AP exam, but it's also one that I want you to just know, because if you're having to use your time to look it up, then you're probably going to be in a little bit of hurt. Okay, so my delta S, therefore, if I'm looking at my products, I only have one product. I have 1 mole of Al2O3. So I'm going to do the S of Al2O3. On my reactant side, I have 1 mole of Al. So I'm going to multiply that by the absolute entropy of Al. And then I have 1 mole of O2. So I'm going to use the absolute entropy of O2. And if you remember from our delta H, when we were looking at heats of formation, we had certain elements that were 0. But but there's nothing that has an absolute entropy of 0, right? So everything has some disorder. And so we're never going to have just 0 for those. We actually have to look them up in a table. So I'm going to look up these values. I'm going to show you how. So that's going to be 1 times the Al2O3. So I look at my table here. I found aluminum. Okay, can't write on it, but I found aluminum. I go over, or Al2O3 is the second one on there. So the Al2O3. I go over to where I see the S. So I see that right there. And that's going to be my absolute entropy. And you'll see that's in joules over Kelvin times moles. I'm going to do the same thing for Al. So that was the first one on there. And I saw that that was 28. And then I also have O2. So on here, I'm going to look for oxygen. So they're alphabetical by element. So I look for oxygen, and I see that O2 gas has an absolute entropy of 205 joules per mole Kelvin, which to me, I look at that and I say, well, that kind of makes sense compared to those other values, right? Because it's a gas, right? The others are a solid, and that's a gas. So I'm going to plug this into my calculator. So that's 51 minus the sum of 28 and 205. And I ended up getting a delta S that is negative 182 joules over Kelvin. All right, so that is my answer for this. I didn't do this before, but one thing that I talked about is, predicting whether it was positive or negative, right? So here, if I look at this problem, we were going from 1 mole of gas in the reactants to 0 moles of gas in the products, okay? 1 mole of gas to 0 moles of gas, that's less disorder. So that's less disorder, and that's actually what we see here. We see a negative entropy value, so that is what we think. Okay, this next one, let's go ahead and do our prediction first this time. We're going from 3 moles of gas in the reactant side to 1 mole of gas on the product side. So think about that. Would we expect our delta S to be positive or negative? Okay, hopefully you've thought about it. So I'm going to go ahead and do my delta S calculation. I'm not going to show all of everything again, okay? So I'm not going to write everything out. So I do know that I have 1 mole of my product, and that product is N2O4. So I actually have it right here, and it says that it's a gas. Be very careful, because if I look at this appendix, there's the value for gas and there's the value for liquid. So I want to make sure that I pick the correct one, and it looks like that is 304. Okay, I also have 1 mole of O2, and so I had that one before, but let me look at it again just to be sure. So that's not O2, dingbat. So N2 is 192. Ooh. And I have 2 moles of oxygen. So if I look at my balanced equation, I have 2 moles of oxygen, and that was 205. So I'm going to plug this into my calculator. And I got that my delta S is negative 298 joules over Kelvin. So hopefully you said that, or hopefully your prediction was that this was going to become more ordered or less disordered, because we went from 3 moles of gas to 1 mole of gas in the products. And so hopefully you guessed or predicted that it would be negative. Okay, so both of these reactions are negative delta S, but they still do occur. So there's two factors that affect whether it's going to occur. We just talked about entropy. We've also talked about enthalpy. Okay, so next class, we're going to talk about how we can combine entropy and enthalpy to determine the favorability of a reaction at various temperatures. All right, thank y'all for listening. Bye, y'all.